Good day, my name is Sarel van Grenen, coming to you all the way from South Africa, and today I would love to speak to you with regarding to stationary points. Now, stationary points, as the name quite rightly says, are coordinates on a graph where a graph is neither increasing nor decreasing, but where the graph is actually standing still. So, for us to know where a graph is standing still, it is very important to just take a step back and to think about how do we know where a graph is increasing or decreasing. Now, the way we know where a graph is increasing or decreasing has to do with the gradient, or the gradient between 2 points. Now, the gradient of a graph is simply the change in y divided by the change in x. Now, this might for you sound like just a very basic and straightforward thing, and it is, but the implications in physics and in chemistry even is extremely important, because even when we look at velocity, it is the change in the displacement divided by change in time. Even acceleration is the change in velocity over change in time. In other words, gradients are extremely important, and a gradient can tell me a lot about a graph, and it can tell me whether a graph, if the gradient is positive, we know that the straight line, that the graph is increasing. Or if the gradient is negative, we know that the graph is decreasing. But gradients and graphs, we would like to work more not between two coordinates, but at a specific coordinate. So instead of working with gradients, we worked with derivatives. Because derivatives, when we think back a bit, derivatives mean the instantaneous rate of change. And that's a very important concept, the instantaneous rate of change. So derivatives gave us rates of change at any point on a graph. Now, a derivative, we always denote it to be either f accent of x, or if we worked with g, it was g accent of x, or dy over dx. Now, we are going to link this directly with gradients. If dy over dx is bigger than naught, it means as the x values of the graph increases, the y values will also increase. In other words, it would mean at that point the graph would be increasing or increasing. So when we have a look at the gradient being negative, we could just as well say that is dy over dx being smaller than naught, which means that as x value increases, the y values decrease, which can lead to a graph that decreases. Or, if we look at x increasing and y decreasing, it could look like this. So when we have a look, let me just do it in red for you. There we go. So when we have a look at this on a graph, here is a graph that I have already drawn for you. And if I look at the rates of change, let's start working from left to right. I'm always going to read like I'm reading a book in English. I'm going to read from left to right. So if I go from left to right, my graph is increasing everywhere that I'm showing you now. But there, right almost at the top of the graph, you will see that it's almost as if the graph starts slowing down. So I can still say that the gradient here, f accent of x, is bigger than naught because the graph is increasing. And then at a certain point, the graph starts decreasing, which means my f accent of x becomes smaller than naught, and therefore my graph is decreasing. And again, it decreases and slows down almost, and then starts increasing again. So my derivative must be larger than naught, and hence my graph is increasing. And now logic would tell me that between bigger than naught and smaller than naught, or between smaller than naught and bigger than naught, I have a point here where my derivative has to be equal to naught. In other words, where my rate of change, f accent of x, is naught, i.e. the graph is stationary. So this means that that coordinate there, the graph is neither increasing or going up, nor is it decreasing. But is there another coordinate on this graph? Well, yes. Right here at the bottom. My graph is also neither increasing nor decreasing. So the derivative is equal to naught. Again, leading me to think that right here at the bottom, I have a stationary point. Well, this is fantastic. Let's move over to another graph and see whether we can find the stationary points. On this specific graph, looks a bit different, but what is going to happen now, again, remember, I'm going to move left to right as if I'm reading an English novel. So on this specific graph, on the left here, my graph decreases. So therefore, f accent of x must be smaller than naught. And here it starts slowing down. And at the specific point here, the graph starts to increase. And it increases and increases and slows down. So here, my derivative is bigger than naught, or it's increasing. It slows down and then it actually goes down again. So f accent of x is smaller than naught, which leads me again to say there and there I have 2 points where f accent x is equal to naught. And again we can say they are both stationary points. Now this is a very interesting concept of the graph, because in these two specific coordinates, both on the previous one, this coordinate there and that coordinate there, both of them were turning points of the graph. The same as with this one. At the left hand, or the left one here, the graph turns. The graph turns on that one. So can we therefore say that all stationary points will be turning points? And for this, at this point of time, you might think that if a coordinate is stationary, it must be turning. And the question is this true, that a stationary point must be a turning point? And actually, the answer is an emphatic no. Let's have a look at the next graph to illustrate my point. From left to right again, here my graph increases, starts slowing down. There, right on the y-axis, it turns, but it doesn't go down again. It just stands still and goes up again. So it actually is not a turning point, although it is a stationary point. And that's a very important concept for you to understand, that not all stationary points will be turning points. But for us to determine the turning points of a graph, I can simply take the derivative and put it equal to naught. And then if I know that the graph turns there, it must be a turning point. So this I want to illustrate for you by looking at a parabola's equation, y equal to x squared minus 4x. So if we look at the equation of a parabola, y equal to x squared minus 4x minus 3, what would the stationary points? What would the stationary points of, or the stationary point, all points of this specific parabola be? Let's get the derivative and let's see. If I get the derivative of this graph, dy over dx, remember, you bring the 2 to the front, subtract 1 from the exponent. So it's 2 minus 1, so it's 2x to the power of 1 minus 4, and the negative 3 becomes 0 when we differentiate. And for it to be a stationary point, we have to take the derivative and make it equal to naught. So if we take the 2x minus 4 and we put it equal to 0, then x must be 2 if I solve for x. But be careful, this is only the x value where it turns. So if we want the y value, we still have to go and substitute this back. So it's 2 squared minus 4 times by 2 minus 3. So by working this out, gives me 4 minus 8 minus 3. So 4 minus 8 is negative 4 minus 3 is negative 7. So therefore my turning point is at 2, negative 7. Now, I'm using the word turning point simply because I know it is a parabola because it's an x squared. So if we had to draw this graph, and I'm going to draw a very rough sketch of this graph. So there's negative 1, negative 2. And then I'm going to have negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. So I know that at negative 2 and negative 7, there I would have my turning point. Oh, I apologize. It's not at negative 2. But at x equal to positive 2. So at x equal to positive 2 and negative 7, I have my turning point. 2, comma, negative 7. And from experience, I know that this is a smiling parabola because it's a positive x squared. So therefore I would know that the graph, if I had to draw a rough sketch of it, would look something like that. Turned there. Turned at that point there. And therefore it would actually be a parabola looking like that. And I apologize for my parabola not being of the best quality here, but it would be a parabola looking like that, which is symmetrical around the x equal to 2. So there, it would be symmetrical around that point. Again, just meaning that the one side of the graph looks exactly the same as the other side of the graph. Now, ladies and gents, this is a very important thing, and this can be expanded to any and all graphs. If you want the stationary points or the turning points of graphs, you simply have to get the derivative and put it equal to 0. And this is for all stationary points. So in future, if you get to a specific point where they're asking you for the stationary points or the turning points of any graph, it can actually be very simple. Get the derivative, put it equal to 0 and solve for x. Now, ladies and gents, please understand there are many applications for this. Now, the applications for this, I would have to look for you in a new video. It can be expanded towards minimums and maximums of any function, of any formula. It could be also later on if you go into calculus and you do differential equations. We use the principle of stationary points on a daily basis. So if you can grasp this lesson and apply it wholeheartedly, I promise you it will open many doors for you. But it's going to be on you to go and practice this now. It's been a pleasure teaching you this. Contact me if you've got any questions or any queries. Have a fantastic rest of the day. Goodbye.